Assalamu alaikum ji. This is our second lecture of the course Numerical Method, which is MATH 351. And in the last lecture, we just revisit uh, actually the content, what are the contents, and what is the requirement of the course. Okay, and we have gone through some of the problems that you may encounter in different portion of the content of this course, and those problems are related majorly with the chemical engineering. So once we are actually doing the um, contents, each content, we will try to address those questions in throughout the course. Okay, so and many more. I've already, by the way, shared with you one problem exercise that hopefully you will be able to do after the end of the next week. Once we are done with the numerical methods for the one variable equation, which were our first topic, so you will be able to understand the procedures, techniques available, and hopefully we will be able to solve those problems. Okay. So today in this lecture we will be starting with the mathematical preliminaries that we required from your previous courses of calculus majorly. So we'll just revise on how to um, round off an information in terms of real numbers, because as we discussed in the first lecture, whenever you implement any particular problem in computer system, the computer system by default have a capacity to entertain on up to certain decimal places. So the remaining obviously portion of the number will be counted in terms of an error. Okay, as we take an example of a root 2, and I have given you that 64-bit systems can handle up to maximum 17 decimal places. Okay, so obviously they are not um, giving us the information beyond the 16 or 17 decimal places. Okay, so but having said that, an accuracy of a 16 decimal and a 15 decimal is a very much high accuracy. Okay, it's not a small in terms of the accuracy we wish to achieve. Okay, but there is an error involved. So we will start with the rounding of the numbers. Okay, um, and then we will go to the Taylor series, which is the second topic that we wish to revisit from the calculus. So in this lecture, we will be focused to just revisit these concepts from your previous studies. Okay, so starting with the round off of the numbers, let's say because we are dealing with real numbers in this course, so let's try to see um, how you round off the numbers and what are the errors that are associated with the rounding of the numbers, okay, of the real numbers. So let me just consider a number, let's say pi. So it is 3.14159. Okay, so I have just written a value of a pi up to certain decimal places. Okay, and because it is an irrational number, its representation of the after the decimal will be infinite. Okay, so this is I have written this number up to certain decimal places. Now the computer understand the problem in the binary digits, in zeros and ones. Okay, it doesn't understand the numbers in the decimal form in which we understand the problem. Okay, so um, to convert this problem into a form that is intermediate between the understanding of the computer and our, there is a representation called decimal representation. Okay, so we are trying to understand the idea of the round off in a setting of the computer systems. Okay, so whenever we have any real number, we try to put into a decimal form, then that number is converted into the binary form. Okay, so what is a decimal form? Let me just take another generic number, generic real number. Okay, so which is x is a real number, 0.b1 B2, B3, so on to bk plus 1, and so on into 10 raised power n. So this is the decimal representation of a real number. Okay, so this number, that is pi, it is not into this particular form. We try to convert that into this form, which will be 0.314159 into 10 raised power 1. Okay, so what idea is, you need to bring the decimal sign in the starting. Okay, and you can use the idea of the exponent, actually, that the 10 raised power, to compensate, to actually move this decimal place at the start of the number. Okay, such that where the number is starting from 0 point and there should be some significant digit. Okay, so this particular number, this b1, b2, and bk's, what are these? These bi's are all what they are, the numbers between 0 and 9. Okay, so they can be 1, 2, 3, 4, whatever, and I from 1, 2 onwards. Sorry, I from 2, 3 onwards. But for the B1, because I'm just writing for the B2, B3, so on to onward. For a B1, this should be between 1 and 9. Okay, so this B1 cannot be 0, because if it is 0, we can just plug some information over here. Okay, so so we have uh, this B1 should be a significant digit in terms of the number between 1 and 9. Okay, otherwise B2 onwards can be any numbers between 0 and 9, any actually integer between. So this must be bi's, must be integer. Okay, so now if we see this particular representation, it is in the decimal form, and this is the decimal representation of a pi. Okay, here in this case, this n value is 1. Okay, now how to round off? For example, we have to round off up to k decimal places. So if, for example, I have to round off up to k decimal places, I will select, okay, the after the decimal point, the k integers, which are, these are the k integers. Okay, and I need to see what is the value of the next integer after k uh, numbers. Okay, so at the k plus 1 position, what is the number? If that number is, if this bk plus 1 is greater than or equals to 5, okay, then the approximation of x, and let's call it as x star. Okay, let's say x star is approximation of x up to k decimal places. Then the approximation of x, which is x star, is given as, so x star will be 0.b1, b2, b3, on bk. So there is an addition of 1 unit at the kth element. Okay, so for example, if this is the number pi and we have to round off up to 5 decimal places, For example, we have to round off up to 5 decimal places. So we will see this representation, which is the decimal representation, will count 5 digits, which are 1, 2, 3, 4, 5. So, and we'll see the 6th digit. It is greater than 5. So pi star will be an approximation of a pi, okay, up to 5 decimal places. It is equals to 0.3141. So the kth decimal will be uh, given an increment of 1, okay, so it will be 6. So this is the approximation of into 10 raised power 1. It will remain as it is, okay. So this is the approximation of pi up to 5 decimal places, okay. And if, for example, this bk is less than 5, then we will not make an increment at the kth position. Then the number will be same as by the kth position, okay. So x star will be 0.b1, b2, b3, so on to bk into 10 raised power n. I forget to write over here, it's 10 raised power, okay. So this will be the representation if at the kth position the number is less than 5, okay. So, but in this particular example, if we try to approximate up to, for example, 3 decimal places, then that number will be 0.314, okay. Sorry, क्या होगा? ठीक है? Sorry. You're right. It's pk plus 1. Thank you so much. Thank you so much. Thank you so much. So you have to look for the index that is um, after the key decimal places that you wish to approximate. So this is a general rule that you normally know from your previous studies. We just want to revisit. What actually consequences of these are is a thing called the absolute error. Okay. So let me just take. Okay, so what is an absolute error? Absolute error is for example, x is the original number and x star is its approximation up to the decimal places, let's say k decimal places. Then this actually, the difference between the two in absolute terms will be an absolute error. Okay, so this is an absolute error. And there is a relative error. So absolute errors are good when there is not too much dispersion in the data. Okay, but they are not a good indicator if there is a much dispersion in the data. For example, some of the values are in thousands and some of the values are in hundreds and some of the values are in decimals, points, small numbers. So then the absolute error will not be a good indicator while handling that data for the estimation of the error. So then the relative error is a good indicator, which is x minus x star divided by the original value. It actually normalizes the error. Okay, so this is the relative error, and if you just multiply with 100, that is called a percentage error. Okay, so let me just write over here. So it's relative error multiplied by 100. and it is called a percentage error. Okay. So for example, if you try to approximate uh, the actual error or the relative error or the percentage error in the approximation of a pi, probably you'll be using the calculators, okay, or maybe a software, we're using a MATLAB software. So we in build we are already using a representation which is up to certain decimal place. For example, on your calculators, you can have a display of 10 to 12 decimal places. Okay. And for example, if you're using a MATLAB or any other software, maybe you can have a representation up to 16, 15 decimal places. Okay. But so if I just calculate the absolute error, it will be pi minus pi star. So this will be the absolute error. And then we have our relative error, which will be pi minus pi star divided by pi. Although pi is an absolute, I have just calculated it. It comes out as 7.34 into 10 to the power minus 6, and this is 2.338 into 10 to the power minus 6. Okay, and if you just multiply relative error with 100, then you'll get the percentage error. Okay, that this amount of percent it is deviated from the original value. Okay, that would be the statement. Okay, so this is just a recap of, you already know a basic information about the round off errors that we will be encountering. Now you see that, for example, whatever the numbers we are using, there must be some error involved in the approximation, because we will be approximating maybe up to 2 decimal places, up to 3 decimal places, or up to 5 decimal places. So obviously we will be rounding off that after those decimal places. Okay. Okay, so there is a slide that will, now look at this slide. Uh, in this example, we have taken some numbers and then their round off values, okay, and we try actually to compute the relative error and the absolute error. If you look at the absolute error and the relative error, you'll see there is a, a different value of the absolute error, but same value for the relative error. Uh, it is happening due to the reason that if you look at the numbers, which is number p and p star, so p is a number and p star is its approximation. So you see that the numbers are from 10 to the power 1 to 10 to the power minus 3 to 10 to the power 4. So the numbers are too much dispersed, okay, in terms of the data. If I just see the first two columns as a data of some information, so the numbers are too much dispersed. Okay, so if they are too much dispersed, then as I already told you, if you use an absolute error, then that will not be a good indicator, but the relative error is. Okay, because relative error normalizes the information, it divides the number by the original number. It's just not the difference between the approximate value and the exact value. It is actually divide that difference with the original number. So it normalizes the information. So if your data is too much dispersed, then the relative error will be a good indicator. Otherwise, the absolute error will be fine. Okay. If, for example, you are, for example, in certain portion of the data where there is not much deviation, then the absolute error will also be a good indicator. Okay. So now coming towards one more thing, just to conclude the round off, there is a terminology called round chopping. Okay, chopping a number up to certain decimal places. So when you try to round off an information, you try to round off up to certain decimal places. But when you chop an information, you don't see what is the number after those decimal places. You just write the representation up to the decimal places you wish to chop. Okay, so for example, uh, For example, I wish to chop uh, up to 5 decimal places the same number, which is pi. So let's say it's pi double star. Okay. So if I try to chop information up to 5 decimal places, I'll count, okay, 1, 2, 3, 4, 5. These are 5 decimal places. Now I don't need to see what is the number after that. Okay. You just consider those, in this case, the 5 decimals, and just write that number. Okay. So this will be 0.31415. You don't need to see what is the number after the 5 decimal places. It's just a concept of a chopping. Okay, just chop up to that decimal place. You don't need to see what is the number after particular decimal places you want to a representation you want to have. Okay, so this is about the handling of the real numbers once we are proceeding towards uh, the methods to approximate the solutions of the equations. Okay, we will be dealing with this information. Okay, now the second concept, if you have any question, you can ask, please. So the round of information is being done on the basis of IEEE codes of how to round off the information. Okay, that's are built in the computer systems. Okay, so we will be following that. The second thing that we wish to revisit is the Taylor series. So what is a Taylor series? Taylor series is the series, actually it's an infinite series that gives the polynomial representation to the functions. Okay, so for example, if you have any function and you wish to have its polynomial representation, then the Taylor series can help you. Okay, provided the derivatives must exist. Okay, so and why polynomials? Because handling with the polynomials is very much easy as compared to other functions. For example, dealing with the exponential functions or dealing with the trigonometric functions. The idea of using integration or differentiation with the polynomials is relatively easy as compared to dealing with the other functions. Okay, so let me just write what is the general form of a Taylor series. If I just write any function, so what we actually require to have a Taylor series, there must be some function f(x). Okay, there is a some point, obviously in some interval, where we wish to open that series. Okay, so this is the information we require. So it says f of x, which will be function that can be written in terms of the polynomial in this way. So I'm just writing the general form of the Taylor series. So on. Okay. So this on the right hand side we have an infinite series. Okay. So that is a problem in a way that you get an infinite series. Again, there come a problem of an infinite. Okay. So once in numbers you see an infinite terms after the decimal, the irrational numbers. Okay. So here you see infinite terms of the series. Okay. But so this is the general form, and if I just write a concise form of the Taylor series, it would be, why concise form? Because we can use finite many terms. We can compute finite many terms. We cannot deal with the infinite many terms. Okay, so that is our somehow limitation, generally speaking. Okay, that is our limitation, not in the particular cases, but generally speaking, we have this limitation of dealing with the infinite. So we try to have its finite representation. So what is a finite representation of a Taylor series? It is f of x naught plus x minus x naught, and it will continue like this, plus x minus x naught n over n factorial, nth derivative at x naught. Okay, and it comes with an error. So there is an error term. I'm just writing over here. It is, let me just write over here. Okay, so it is x minus x naught power n plus 1. So rather than x, we have another thing now, which is alpha, for example, any number, and it will be between x naught and x. Okay, we try to see what is this, but if you just see the n terms, this is the finite representation of a Taylor series, and this is the associated error. Okay, so whenever we talk about the approximation, there is some associated error. Okay, when we try to approximate the pi up to certain decimal places, there is some absolute error that is connected with that. Okay, so whenever we use the concept of the approximation, there is an associated error with that. Okay, so when we try to approximate through the Taylor series, there is some error that is obviously with that approximation, because we are using finite many terms. If we are stopping at a finite many terms, we are ignoring many terms. So those ignoring terms must have some value. Okay, so we need to quantify that, what amount of that value possibly be. Okay, so let's take an example and try to understand this. Thank you so much. Thank you so much. This is yes. Thank you so much. So this is the finite representation of any function. Let's take an example and try to understand this. Okay. So I'll consider a function f of x, which is e power x, and x naught is 0. Okay. So the function is e power x, and the point x naught we wish to open the series is 0. Okay. So what we want is, we want a polynomial representation of e power x. Okay. So if I see, for example, the first generic form of the Taylor series, it requires a derivative to be evaluated at x naught. Okay, and fortunately, the derivatives of e power x will be e power x for every n we have. Okay, first derivative or second derivative or any derivative. So if I plug the value x naught, it will be e x naught. So e power 0, this will be 1. Okay. Now if I use the value x naught in the generic form with the derivative values as we evaluated, so let me just write the generic form. So f of x, which is e power x, is equals to f of x naught, which is 1. Because if I just evaluate x equals to x naught, it is e power 0, it will be 1. So this is 1 plus x minus 0 into 1. So it is simply x. The next term we have x squared over 2 factorial. Okay, because this value is 1 and here we have a 0. Okay, so if I keep continue, this is the representation we got. Okay, so this is the Taylor series of e power x about a point x naught. Okay, so now let's take the finite representation of e power x. Okay, which is this. So I can write over here ex is equals to 1 plus x plus x squared over 2 factorial plus nth term is what? Nth term is x power n over n factorial. And here you see, we have, rather than x naught, we have alpha here. Okay, so if what will be the nth derivative with respect to x? It is e power x. Okay, and if I replace x with alpha, what is this? E power alpha. Okay, so this is the nth term, and the final term will be, the error term will be x n plus 1 over n plus 1 factorial and e power alpha. Okay, so I just write these terms, and the error term is over here. Okay, this is the error term we have. By the way, probably you have seen in your previous courses x n over n factorial. Maybe this is the infinite representation of e power x. Okay, so this is the series. Okay, so but since we can have finite many terms if we wish to evaluate, so that's why we're just taking the n terms, for example. Okay, so we just take the n terms, and what is this? This is a special term. This term, it will give us the error estimation involved in the approximation of e power x. Okay, so it will give us the approximation of how much amount of error is involved if you take this representation of e power x. Okay, now let's try to have derivative. So we have a question. We are taking a derivative of a function which is e power x. Then we plugging the value x naught. First we taking a derivative with respect to x, and then we plug the value x equals to x naught or x equals to alpha. Okay, first we have to take a derivative, then we need to plug the particular value that we wish to plug in. Okay, so this is the error estimate of this equation. Okay, so let's say I just write over here a question which is, let me just have a space over there. So let me write a question which is approximate value of e, which is a number exponential power 1. Okay, uh, using first, second, third, fourth degree polynomials. Okay, let's try to approximate the value of e. Okay, so if it says it's a first degree approximation, let's use a first degree approximation. It means you have to use a polynomial up to first degree. Okay, first degree polynomial, which are straight lines. Okay, so what will be the approximation of e power x? It will be, approximation will be 1 plus x. So that will be the approximation if we're using a first degree. Okay, so this is a first degree approximation. Now we wish to have the value of e. How can I have a value of e? By plugging the x value as, but I can plug the value of x to get the value of e. What is the value I need to plug over here? I need to have the approximate value of e. Okay, what is the value of x I need to plug here? 1, 1. It's 1. We just need to plug. So let's use x equals to 1. If I use x equals to 1, e will be 1 plus 1. So this is 2. Okay. So if you go to your calculators, you have an idea okay, um, how much the value of e will be. Approximately, it will be 2.71, such a value. Okay. So what is this, by the way? If I just omit the approximate sign, this is the approximation of e. Okay. This is the approximate value of e. Okay. Approximate value of e. Okay. So what is the error? E minus e star. So this is the absolute error. Okay. If any one of you go to the calculator and just write e minus 2, so it is 0.71, this much of value you'll get. Okay. And if you just divide by the value e, what is this? A relative error. Okay, it's a relative error now. And if you multiply that with 100, what you got? A percentage error. Okay, can any one of you give me a what is the percentage error? Just subtract the 2, which is e minus 2, and divide by e, multiply by 100. It's 26.4%. Okay, so this amount of percent a deviation of e and e star. Okay, so that is the deviation of e. Now let's increase the order of accuracy. Let's use a second degree polynomial. Okay, because e power x is actually the infinite degree polynomial, and we just trying to approximate by the finite many terms. Okay, so if for example I choose the second degree approximation, this was the first degree, now the second degree is e power x is approximately equals to 1 plus x square over 2 factorial. And if you plug x value 1, so it will be 1 plus 1 plus 1 over 2 factorial, which is 2.5. Okay, it is 2.5. Now this is what? This is again the approximation of e, but with the second degree polynomial. Okay, so we're trying to increase the order of the degree. Okay, order of the polynomial we just have. So this is again an e star. I'll just call it e star because it is an approximation of e. Okay, we'll understand that. Okay, it's not the power of e. So if I calculate the same term, which is a relative error, you will see we'll get approximately deviation of 8%. Okay, we just need to subtract in this way, and so you'll get the percentage error. So we have a deviation of approximately 8%. Okay. Now, if you can see on the slide, okay, if we just take the approximation up to third degree, uh, how much percentage error we will be having? So it is approximately 2%. Okay, approximately 2% error we're going to get. I will be requiring this information. So let me just write for you that if, for example, I take a third degree approximation, which is 1 plus x square over 2 factorial plus x cube over 3 factorial. Okay, so the answer will be 2.667 approximately, and I get an error of relative error of 1.8%, or approximately a 2% deviation. Okay, so So and if I just go to the fourth degree polynomial, you will see a deviation of approximately 0.3%. Okay, so what we are getting is that as we are increasing the order of the polynomial, in other words, we're trying to compensate the more terms from the right hand side, our accuracy is getting better. Okay, we are getting near to the value that we wish to approximate. Okay, so so there will be a point where we will decide that okay, that much amount of the right hand side or the polynomial is sufficient enough to give us the accuracy, because you see the relative error, the fourth term is becoming as 0. Okay, so 0.3%, so it will be going down. And so it is also a conclusion that we can draw why we have to deal with the infinite many terms if they are not contributing that much. So then the finite representation is a good way to go with. Okay, and dealing with a polynomial is easy as compared to dealing with e power x. Okay, so because from e power x you can go to e power x squared, you can just replace x with x squared. You can replace x with x cube. So you can replace the function and you can increase the difficulty in terms of the exponential functions. And you on the right hand side you're just dealing with the polynomials. Okay, so uh, I'll just try to conclude that in the Taylor series, what we are actually doing, we were doing actually to approximate the function in terms of the polynomial. Okay, and then evaluate whatever our goal will be. Maybe the integration, maybe to solve an equation. You just see a functional representation of different functions. Okay, that is a polynomial representation of different function in a finite many terms. Okay, now one thing which is just missing, that we have not just what is this error estimate? Okay, we are just calculating the error in each approximation, but what this error estimate is. Now let's try to just discuss this, and then we will be done with the Taylor series. So the error term. Let me just write a question, and through the question we try to understand this. Okay, so approximate the maximum error involved in approximation of E with fourth degree polynomial. So we have a question and we try to address that question and try to understand what this error estimate is. Okay, so this term is always there, and if you see this term will be a uh, next term up till the degree you want to approximate. For example, if we just wish to have a first degree approximation, then the error term will be the uh, third term. Okay, if we just wanted a second degree approximation, then this will be a 1, 2, second and a third term, sorry, fourth term. Okay, so the next term will be the error term. Okay, so the next term is an error term. If for example I want a fourth degree approximation, then what is a fourth degree approximation? Let me just write over here. The fourth degree approximation of e power x is 1 plus x square over 2 factorial, x cube over 3 factorial, and x4 over 4 factorial. Okay, what is the next term? Next term is the error term. Okay, it is the term that gives us information about the error. So it is x5 over 5 factorial e power alpha. Okay, it is e power alpha. Okay, so I'm just now don't need this, so I have its finite representation. So it says, the question says, uh, when you try to approximate e, what is the maximum error we can have uh, with a fourth degree polynomial? Okay, so this is the, if I just write this in another form, ex approximation is just 1 plus x square over 2 factorial, x cube over 3 factorial, plus x4 over 4 factorial, with the error which is x power 5 over 5 factorial e power alpha. Let me write with the error bound, okay? Rather than error, I'm just using an information error bound. Okay, so when I try to approximate e, what is the value of x? It is 1, okay? And if I see an error term, the error is equals to, let me just write equals to, then it is 1 power 5 over 5 factorial e power alpha. What is alpha? Alpha, if you remember, alpha is a number between x naught and x. If you just go to when we started this, alpha, I just write over there, if you go to your notes, alpha is a number between x naught and x. Okay, what is the x naught? X naught is a point where we open a series, which is 0. Okay, so alpha is a number between 0, and what is the value of x? We just choose this one. So alpha is some number between 0 and 1. Okay, so if this is the error we got, we need to quantify it. Okay, so I'll say that this is less than this value is less than which value? E power 1 over 5 factorial. I just want a maximum value of e power alpha, because I wanted a maximum error that can occur. If alpha can go from 0 to 1, it can have any value between 0 and 1, and I want an error bound. It means I want how much maximum error this approximation can have. Okay, to find this, I need to have a maximum value of an error. To get a maximum value of an error, I need a maximum value of e bar alpha, and alpha is coming from this interval. So what is the maximum value of alpha that can give me a maximum value of e bar? What is the value of actually alpha that gives me maximum value of e bar alpha? It will be e power 1. You can say that it can be 0.99 or 0.999, for example, 0.99. So if you say 0.99, I can say there is another number which is bigger than that, which is 0.999. So if you say that, so we will be just discussing in a fight that will not be end anyway. So that's why I just put a sign rather than equality. I just put a sign less than, strictly less than, and I just plug a value 1. Can you please give me the value? What is the answer of this? 0.65. So this is, so what is the answer? In the approximation of E, this is the maximum error I can get if I approximate up to 4th degree with the 4th degree approximation. Okay. Now, if you compare this error with the error that we got in the 4th degree, it is approximately 0.36%. Okay. So if you take a 0.36%, it means it will be 0.0036 in terms of the value. Okay, so it will be less than this value. This is the upper bound that we got. Upper bound. It is the maximum we can have in error. So there are two things I just wanted to differentiate. One is the absolute or the relative error, and other is this error. This error is called truncation error. Okay, we have a terminology for it. It is called the And what is the basic difference between the two? truncation error is being derived from the function, from a function. Okay, there is an involvement e bar alpha. Okay, so we derive the truncation error from the function. Okay, a functional representation, and the absolute error or the relative error are determined through the numbers. Okay, from the numbers. Okay, so the both are the errors, but the absolute errors are connected with the real numbers, and the truncation errors are one which are connected with the functions. Okay, so there is a difference between the two. So in the Taylor series, when we're talking about the error, it is about the truncation error, and when we normally talking about in the numbers, it is the uh, absolute error or the relative error or the percentage error or the summation. Okay, so um, so if you have any question, you can ask from this Taylor series. We just see in the Taylor series that how can we write a function in terms of a polynomial, and how we can approximate the value using the polynomial representation. Okay. Okay. So okay. Last part कौन सी? Okay, you see यहाँ पे we have the value, and we are dealing with the numbers now. Okay, but in when we try to find the error bound, we use the functional representation. So error is being in the functional form, in sort of a function, and then we find the maximum value of that function. That becomes the truncation error. Okay, so just to wrap up this lecture, in this lecture we just have some preliminaries from the calculus, which is just how to round off the numbers, because we're going to put the algorithm into the computer system, and we have those errors coming up with us. And the second thing is the Taylor series, and in the Taylor series we just see how to convert any function into the polynomial form, and how maybe we can approximate through, and the error associated with the Taylor series is the truncation error. Okay, so in the coming up lecture, we will be going into the actually intermediate value theorem, and which will help us in going to our topic number 1, which is the solution of the one variable equation. Okay, thank you so much.